Hi, hello, and welcome to section. Thank you all for being here on time, like me, to section number 7. So, announcements things. Today is the last day for regrade requests, so if you have them, please submit them. So far, we've only gotten one. Regrade requests are fine. Like, I know I had my little announcement of just like, don't do a regrade request because you feel like it, but like, I have made mistakes. I do. I'm fallible, as you clearly know. Second one, mid-semester check-in meetings. So I've cleared 14 hours next week to meet with you lovely people and do like little one-on-one meetings. The sign-ups for that, the first batch went out this morning and then they'll go out over the next couple of days. It's really just like a chance to like meet with y'all one-on-one and be like, hi, how are you? What would you like to talk about? And it's anything related to the course, or if you just want to chit chat. I, in the email, give like a very, very rough, vague, unofficial grade update of like, based on how you performed on the exam, students who have gotten similar things in the past have scored between this and this. And it's like a huge grade. Yeah, like it's not really that helpful. Don't take it too seriously, especially because a lot of things can change. But then I have tiered it to go out based on your exam 1 scores. So the people who scored a little bit lower get first dibs at sign up just to like prioritize that. But I would like to meet with everyone. So please sign up for a slot. I'll be in the Smith Campus Center near the Mother Juice with the big glass wall in Holyoke. It's going to be cold. You're going to be there for 10 minutes, but it's going to be cold. So bring a sweater if you need. Yeah, I think that's that. Mid-semester feedback. So as I checked last night and about half the class had done it, and our goal is 85% for the little like bump for exam 2, which will probably be like 5 points added to everyone's individual score, like something along those lines. Not percentage points out of 150, like it's a very small bump. But like some of your students get to the 85%, sometimes they don't. So if you would like to get to the 85%, tell your friends. Yes, I think now we're about 50%. I'll send an announcement out on Sunday and say what percent we're at. Yes, we read them a lot and we like make changes based on them. I think I talked about it a little bit before section 6, but that's kind of logistic stuff, big picture. Also, people keep missing their quizzes. I'm so sorry. People keep forgetting to do the quizzes. So please remember the quizzes. They're so small. So small. Should be easy points. Yeah, any logistic questions? Work. Game plan for today. So, there's a lot of stuff, and again, I don't like it that much. So what I'm going to do is I'm going to start off with carbocations. We're going to go a little deeper on that and see some of the weirder ones on the problem set, because I think that that's going to be helpful, because otherwise people start to just do crazy like carbocation things. We'll talk about making alcohols leaves. We're going to do a light touch, if you will, on ethers and epoxides. And then the last 30 minutes, we're going to talk about how to study reactions part 2, the remix, where we talk about some strategies for kind of learning the basics of reactions so that you can do the higher order problems. And then we will do a synthesis question, that I think is like challenge problem 10. And that will probably take like 15 to 20 minutes, but I would like to do the whole thing because it's the hardest synthesis you've seen so far, and I think it would be helpful to do it together. So, oh, I need one more thing. I forgot. I'm so sorry. My little soundboard. Because what else would we do if we didn't have our transition music? Okay, we are in the section 7 soundboard. Let's talk about carbocations, which she was our QR code for today. I don't know if you spotted her. So we talked about in lecture 6 that carbocations are stable via hyperconjugation. We love to see it. So hyperconjugation is the sigma bonds next door leaning closer to the carbocation, going there. I'll put my electrons a little bit closer to you, just a little. And we talked about tertiary carbocations are the most stable here. Then the secondary, we also have resonance stabilization. The big idea with carbocation rearrangements is if you can form a more stable carbocation, you will. Like, it's that easy. And the two biggest ones that we want you to be able to recognize here are the hydride and the methyl shift. So if you have a secondary carbocation adjacent to a tertiary carbon, then on this tertiary carbon there should be a hydrogen, and the hydrogen with its electrons, so in other words a hydride, will shift over to where the current carbocation is, and that will make a tertiary carbocation. Similarly, if you have a secondary carbocation adjacent to a quaternary carbon attached to 4 other things, then an entire methyl will shift over. And then again, you will create a tertiary carbocation. In both cases, you are going from a secondary carbocation who has a complicated neighbor to a tertiary carbocation. You're becoming more stable as a molecule, so that is why the shift happens. If there is no reason for it to get more stable, a shift is not really going to happen. So anytime that you are forming carbocation, it's like you're crossing a busy road. You need to look both ways for potential rearrangements before you cross the street. Otherwise, you're going to get hit. You're going to hit on the exam. So these are the ones that we want you to know and predict, and these are fair game for like line reactions, synthesis. But the world of rearrangements is huge. And there are so many that you can't really predict, like you specifically. Other people can, but like it's just too new. There are crazy ones. There's some where they jump over like 13 like atoms, like they form a big ring and then just hop over, and yeah, it's stuff of nightmares. So we are going to talk about some of the kind of next steps of the rearrangements that are a little bit more complicated than this. That involve typically an alkyl group shifting, so something bigger than like a methyl. So any questions on these basic rearrangements? Okay, I guess it's time for, and if my sound cue would work, the stranger rearrangements. So, first up, let's look at this one with HBr. Y'all started talking about alkene reactions, and alkenes are going to go and grab a hydrogen if they are an acid. Now, when we do that, we have an option. We can either put the H on the right side and put the carbocation on the left side, or we could put the H on the left side, carbocation on the right side. Which do we want, carbocation on the right or the left? Left. The left, because it's going to be much more stable. So, blum, 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 carbocation. Now, you can draw the hydrogen here, but also, like, we know that we can imply CH bonds, so at your comfort level. So now, we have a secondary carbocation adjacent to a quaternary carbon, right? So I think a logical thing that you could think is maybe there's a methyl shift that can go over. That would be totally reasonable to expect. The other thing to be aware of is here we have a 5-membered ring. 5-member rings don't have crazy strain, but they have enough strain that it is like appreciable. So one thing that it can do, and Logan mentioned this, but I don't think he showed an example, is we can actually have the sigma bond in this ring do the shift. In this case, we would call it a 1,2 alkyl shift. In other words, a ring expansion. And now, when we have that, we are going to be creating, let me kind of number this a little bit for you. So it's going to be 1, 2, 3, 4, 5, 6. We form a 6-membered ring. And I'll do 1, 2, 3, 4, 5, 6. On carbon 1, what do we need to have on it that's not currently drawn? We need to have a methyl. Then, on carbon 2, what do we need to have? Another methyl. Yeah, and that's the other thing. So, to figure out where a cation, look at our original molecule here and ask, who did we just rob? So, this had the carbocation. This boy left with the electrons. carbon 2 was robbed of electrons. So it's going to have the carbocation after the fact because we took away a bond from it and we didn't replace it. So now we have a carbocation in a 6-member ring, and this is also a tertiary carbocation. So this is another valid move that we could make. And then the step 2 would be the Br minus coming and attacking here. I think normally I do like 2 options on this. Like I show you could do it like this, or you could do it another way. So what is the option I normally show? Oh, I also just show like what it would look like with a methyl shift. So if instead we just decided to do the one like we've seen in lecture and shift to this way, then we would have a 1,2 methyl shift. We'd still have our 5-membered ring, but now we'd put our carbocation here. And again, it's a tertiary carbocation, and then our Br minus can come and attack. Work. So that's one idea of something that we can do that can slightly mess with the rearrangements that you've seen. But do you see that's kind of in line with principles of like we're forming more stable molecules, which is why it's allowed to do these reactions? Is that okay? Okay, another one is if you have a secondary carbocation adjacent to a 4-member ring, she must be expanding. She must be expanding immediately. So again, we are going to locate the sigma bond in the ring that's adjacent to the carbocation, and that's going to shift over and make a 1, 2, 3, 4, 5-membered ring. And then on carbon 1, we have a methyl. Who did we rob? Well, 5 went from bonding with 2 to now 5 is going to bond with 1. So we've robbed Miss 2 over here. And honestly, you could think about this one moving instead because it's going to be symmetric. So, yeah. So now it's going to be 2. But, ooh, we have a more stable ring. But what type of carbocation is this? Primary, secondary, tertiary? Secondary. And, oh no, we're next to a tertiary carbon. So what could happen? Hydride shift. There we go. So we have 2 shifts here. We're feeling rather shifty. So, yes, you can combine and have multiple rearrangements like this. Then, challenge problem 6. At some point, you are going to get a carbocation that's big up here on this like crazy bad boy. This is kind of an FYI, and to be so honest, I don't think it is. Oh, no. Actually, this does affect the question. So here we have this bridge on our 2 rings, and that leads to a fair degree of strain. And so if we can get rid of a bridge, that's another thing that we will try to do. So let's look next door at a sigma bond. And let's do an alkyl shift. Now this thing, when we try to write out the next step, it's going to look horrible. And this is where I love the numbers game. So let's number how it exists here. So we don't have to anymore. But let me show you, because there are several ways that you can do it. So we have a 1, 2, 3, 4, 5, 6-membered ring. That's this bad boy. So there is a 6-membered ring. But then there's also another 1, 2, 3, 4, 5, 6-membered ring here. And so it's like they glued like 2 chairs together. So let me just actually number all these carbons. 7, 8, 9. Yeah, so we have 9. And if I did my rearrangement, now I've broken 2 to 9. And instead I've created a 1 to 9 bond. So did I mess with this 6-membered ring at all? all those bonds stay intact. That 6-member ring is going to be there. So when we draw our answer, let's start off by drawing a 6-membered ring. And then I will number them. So I'll do like 1, 2, 3, 4, 5, 6. And now 6 is still connected to 7, 7's connected to 8, 8's connected to 9, but 9's connected to 1. So if we look at that, we have 1, 6, 7, 8, 9. That looks really funky. How many carbons is it? 5. No, 1, 2, 3, 4, 5. Because, and again, I'm drawing it as if we had just done the shift. So it has like collapsed a little bit. So what I'm going to do is I'm going to draw a 5-member ring. And then we see 6 is still connected to 7, 7 is still connected to 8, 8 is connected to 9, but now 9 is connected to 1. So again, this is where I think this numbering strategy, if you're ever dealing with rings or 3D things, can be very, very helpful. Because otherwise it's really hard to be like, oh, I guess I can go from this to this. Now, who did we rob? 2. We robbed 2. So, this is what's going to finish off the reaction in the problem that we give you in challenge problem 6. Like, then it's going to do like some sort of like SN1 thing or an E1 thing, and like a acetal something that's going to like come and attack here. Sure. But hypothetically, this is a secondary carbocation, and what's it next to? Tertiary. So she could hypothetically rearrange again. But for this reaction that we actually gave you, where we showed you the products, you will see that it did not shift. And so you only need to account for the rearrangements that get you to the product. Like, even if it could do other things, like, we don't care as much. Yeah.
For the one above, which products do you prefer? Will you take those then?
So this is the thing. Like, we wouldn't ask you that on an exam without us giving you the product. We would want you to be able, if we give you the product, to figure it out. But I'm thinking, putting it out this way, just so that you get practice thinking through it from the beginning. Just because otherwise I think it's hard to build on. Yeah.
Wait, why did the carbon-cation move from 1 to 2?
Because 1 just got another bond with 9. So it has, 1 has a hydrogen up here, these 2 bonds, and now it has a bond with 9. It's a hydrogen, so full octet. But then 2, it did have a hydrogen over here, 2 bonds, and then this bond with 9. But now 9 took its electrons and left. And so we've robbed 2 of the electrons.
Okay, alright.
Yeah.
This might be, the answer to this might be just like, that's just what we observe. But why would a hydrogen not shift?
That's just what we observe.
Okay.
No. It's a great question. Yeah.
And for problems like these, it's kind of only going to be like, find a mechanism. It's not really going to be a major part.
Yeah, typically you're only going to do the rearrangements in box problems or synthesis if they are this simple. Occasionally there might be one that's like a ring expansion. Occasionally. This type of thing would never be on anything that wasn't a mechanism question. Yeah. One more. So challenge problem 3 is weird. It just is weird. It says, this carbocationic shift is observed to occur simultaneously with the departure of the leaving group. In which case I'm like, it's not carbocationic, it's just a rearrangement. But I didn't write the question. So basically this is saying the leaving group is going to leave and a shift is going to happen at the exact same time. So if we look at this molecule, what do we think is our leaving group? N2. She'll bubble off as N2 gas. It'll be really, really exothermic. Lovely. Okay. So if she leaves, we're going to have this arrow at some point. Then maybe we need to think about, okay, if a bond broke, where do we put electrons? In the antibond. So if our bond here is this sigma Cn, where we have the big lobes here, that's the bonding orbital, then the antibonding orbital is like this. what do you see as parallel with that antibonding orbital? This methyl over here. So let's try it out. Let's try it out. So we are going to do this methyl shifting at the same time as our leaving group leaves, which again is weird and new and something you haven't seen, and it's just a quirk of this question that you probably will never see again. But that's what it's asking about. So if we do that, this is kind of weird. So initially, we had a hydrogen over here, right? And imagine our hydrogen's like up like this, and our methyl's coming next door and going blah. So it's going to rotate it down. So in the equatorial position that's up, we're going to have the thing that came from up, which was the CH3. And then in the down position, we have this hydrogen. And again, it's like we have our methyl next door, we have our hydrogen up, but when she shifts over, then they shift down. So the methyl is equatorial up, and the hydrogen is now down. We can see a high quality animation of that. So when she shifts over here, do you see how this CH3 is more up than the hydrogen is? So when this girl down here leaves, these two are going to just rotate down into the normal positions for the chair. Again, this is the type of thing that I wouldn't expect you to predict on your own, but in seeing it, we want you to be able to understand it and kind of put the pieces together. You look upset by that, Chelsea. You said, yeah, I am. Thank you.
I usually am with these guys.
That's okay. That's so valid. That's very fair. Now,
Is the orange down?
who did we rob?
The carbon.
The carbon. And ooh, what's her hybridization? sp2. Because she has an MTP orbital. So I intentionally wrote her as neither equatorial or axial. I almost said equitaxial or something. Like, yeah, it's weird. It's a rough time. But is this a good carbocation? It's a trap. It's a trap. We have resonance. Resonance. So it's actually very, very good. It's actually very, very good. Blom, blom. Blom, blom. Okay. So, with this, our resonance structure, we have complete octet. So is that good?
Yeah.
It's fierce. So even though it looks like a secondary carbocation, it's better. It's better. And so now, to get to our product, all that we have to do is a deprotonation. So something's going to come over and grab this. So another thing that you'll see as a theme of this problem set is we are wanting you to get more comfortable with seeing things in chairs and perspective and multiple chairs and 3D. Yes, it's kind of a thing of like, if we want to make you feel uncomfortable on an exam, we'll write something that looks like a crazy ring. And your strategy is be ineffable. Really see that and be like, okay, I can count things. I can number. Like, have your strategies and focus on the reactions, and it being a crazy ring thing should not mess things up. But it just looks scary.
Can you explain again why that OH became plain?
Yeah, so this carbon had 1, 2, 3, 4 bonds initially, right? So she's normal, sp3 hybridized, she has a full octet. But then when this methyl leaves with her electrons, they go over there, we have robbed this carbon, of electrons. So she only has 3 bonds now. So she has an incomplete octet. With me so far?
Yeah.
So if we have an incomplete octet, we have an MTP orbital, which means that we are not hybridizing this 1p orbital. So if we have spp and we are keeping one lone, we hybridize sp2 over here, and sp2 hybridized is planar. Yeah, so it's a lot of like little steps. Yeah.
Going back to like the first movement of the
is it going down to the actual position again just because it's like sterically preferable, or is that just always what's gonna happen with like moving?
Wait, when you say down to the axial, like it becomes the equatorial position.
So, I'm sorry, can you explain that again?
Yeah. So it is this CH3. When she comes and moves over, do you see how she is more up than the hydrogen?
Yeah.
So when the leaving group leaves, these two are going to shift downward, but the CH3 is still going to be more up than the hydrogen. So the CH3 is more up than the hydrogen, and this kind of rotates down. Is that okay-ish?
Yeah.
Yeah, it sucks. I'm sorry.
And that's our most stable chair.
Yeah. Yeah, because, like, I mean, I guess we could, for a brief moment, consider a chair that's written like this. But if she's like that, she's going to want to relax those bonds to the normal, like, bond angles. And so it'll rotate down. Yeah. Yeah. So this has been Stranger Rearrangements. Thank you all for coming to my TED Talk. Yeah, you'll see more. They are uncomfortable. And then when you miss one, you feel like, whoa. That's just the nature of them. Cool. Any questions on rearrangements before we go on? Party. So, we need to get alcohol out of here. What? So alcohols are problems for us. They are not good leaving groups. So if they are invited to the party, they will never leave up until this lecture. We need to figure out how to get them out of the vicinity. So a half-baked solution, which is a strategy, you can use it, but is just be careful. Dump the alcohol in a vat of acid is basically the strategy. So if you put it in concentrated hydrobromic acid or hydroiodic acid, iodic, sorry about that. If you put in a super strong acid, then you essentially get either an SN1 path or an SN2 path, depending on if you're tertiary or if you are primary. So tertiary, you protonate it, and then you're on a tertiary carbon, so the leaving group can just leave. So you get a carbocation, and then a bromine can come and attack. Now you have a good leaving group on there. You have effectively kicked off an alcohol. Now, if you do it on a primary alcohol, then what happens is you do OH2 plus. Instead of the leaving group leaving, because that wouldn't form a stable carbocation, the Br minus can then come from behind and do an SN2 backside attack. So, like, using SN1 and SN2 chemistry in new ways is the theme of Lecture 7. And so, yes, these will turn alcohols into alkyl halides. But what about secondaries? This is going to be fair for both secondaries in terms of carbocation stability and in terms of steric availability. And then also, like, if you have a molecule that has any other functional groups on it other than your alcohol, you could easily be in trouble because exposing your molecule to strong acid can cause other reactions to happen that you don't want. So we need some safer alternatives. Here are safer alternatives. So we have tosyl chloride, SOCl2 and pyridine, and PBr3. These turn alcohols into either OTS, Cl, or Br. And the big thing that you need to keep in mind, the reason why we have multiple of these for you to learn instead of just one, is to pay attention to whether or not stereochemistry is retained or inverted. So over here, you have an alcohol that's on a wedge, a secondary alcohol, which we said is not going to be good for the strong acid approach. It's going to be fair for both SN1 and SN2. When we add our tosyl group, our tosyl chloride, then this oxygen is going to be the one that does the attack over here and kicks off the Cl. So did we change the stereochemistry at this carbon down here in the box? No. So no SN2 happened on this carbon, so we have a retention of stereochemistry. The other one that I think students get confused on a lot is that this O is going to be the O in the OTS. Like, that is the same oxygen. The only step that we are missing when I like write this out of like attack and blah blah is we're missing a like protonation step. So it'll be like OH plus and then something in the solution is gonna deprotonate it. Blah. So that version retains our stereocenter. SOCl2 and PBr3 on the other hand have a step where our halide is going to do an SN2 attack on the carbon. And because of that step where the halide does an SN2 on this carbon, we then get our halogen added on a dash instead of a wedge. And so we get inversion for these two. Yeah.
Previous part, when it says no SN2, you're not saying that you can't do SN2 on that thing once you make it. You're saying that you don't use SN2 to make it.
That's exactly correct. Yes. So I'm saying in the process of making this, we did not do an SN2. Whereas in the process of making these, we did do an SN2. Once we have made these can now enter our GFP game. They can do SN2 or elimination or whatever because now we have good leaving groups in place. Whereas before, when we were doing lecture 6 stuff, you only really saw reactions with alcohols when you were doing like an E1 with like conc H2SO4. So now we can add alcohol to the party. So our key question, do we want to retain or invert the stereochemistry? So you did an example a little bit like this in lecture where it's just kind of drawing what the products are of things. I've also done a version where I'm asking you to supply reagents for what to do. But the key to this is looking at the wedges and dashes. So I'll do the first one with you, or no. Which one do you want me to do? First one, second, or third? Oh, okay. We're the only person with a strong opinion here on it. So, let's see. Right now, I see I start on a wedge and I end on a wedge, right? But I see that I have a new nucleophile that's like been installed here. So I've definitely done one SN2. So if we want to do one SN2 though, it's going to be on a dash. And then if we do a second SN2, it'll go on a wedge. So with this, let's see, what would be a good nucleophile to accomplish this to add N3? It seems like a trick question, but it's not. It's N3, she'll have a negative charge, so we need to add an Na. NaN3. And then we need a version of it that has a good leaving group, and we want that leaving group to be on a dash, right? So what are our methods of going from an alcohol to a leaving group on a dash? Can we use tosylate for that? No, we can't use tosylate, so we have to use SOCl2 or PBr3. Pick your favorite. I'm going to do PBr3. Oh, and that, like, I'm not acquainted with beer culture, but I do think PBr is a type of beer. And so I think, like, alcohol, if you want to make the alcohol leave, you get a PBr. I don't know. I don't know. I have no idea. I didn't know that there were types of beers, if I'm going to be so honest.
No, same, but like...
Yeah, I've heard of stouts, but I don't know what that is. I've heard of sours.
Yeah, but like this is an inorganic thing, right?
This is not real alcohol. This is just PBr3, the molecule, and it's just the same name, I think. Yeah, I don't know. But any mnemonics, like our Tina Fey hates chicken, like anything that makes it stay, live and let go. Tina Fey.
Oh.
Because it removes bog. Tina Fey hates chickens. I love it. So, I'm going to let you work on this for a minute or two, and then I'll answer some questions. Yeah.
Why would you give us two options for the inversion then? There must be a reason for choosing one over the other.
Chlorine's a worse leaving group, right? In certain.
To be so, like, yeah, there are, like, little distinctions, but it's just kind of like, sometimes you might want a bromine instead of a chlorine. I don't know. Sorry. Well,
Just two reagents to memorize instead of just one. And we could have accomplished anything we wanted with just one.
but if we want the product to have a chlorine, there's only one thing that you can use. So. believe I got the plastic off my eye. I really thought that's how I was gonna live.
On your eye patches.
The way I was considering hobbling and being like, hey, great to see y'all.
Wait, what happened?
My contact split apart on my eye this morning when I put it in. Like, you can probably see my eye is still red, right?
But is it like, do you use disposable or?
I do. And so it shouldn't be as much of an issue with disposable. But then it was sealed on the eye. Like, I couldn't get it off. I could feel it. And she said, I'm not going anywhere, sweetie. She really said, my feet are planted. Mm.
What reagents could lead to SH on there?
What reagents could what?
Like, could lead to SH
Oh.
on the last one?
Nash. N-A-S-H.
Oh.
You just put NA, like.
Yeah.
Yeah.
Yeah. That's kind of the yeah.
Wait, that's it?
And then do we have to put what it's dissolved in?
No, not for this.
Thing.
Other than SOCl2, you have to. SOCl2 pyridine. But when you're doing just a general, like, SN2, our class does not test solvents very much. So, like, alcohol versus DMSO, don't worry about it. Yeah.
So how do you can use NA but then use KCN? Why is that not MACN? Like when
You
go
can.
to-
They're both fine. Yeah. Generally speaking, anywhere you can put an NA, you can put a K. For our, like, reagents as just a counter ion. Yeah. So it seems like we have a fair amount of good work on this. So let's talk about the first one. We have an alcohol on a wedge, SOCl2. So replacing an alcohol with a Cl. And did an SN2 happen here?
Yes, because it's
Yes.
inverted.
So we invert the stereochemistry. Then, is an SN2 happening here?
Yes.
Yes.
Yes. And this is set up as if it was just, oh, more SN2s. What if I put MEO minus? Did an SN2 happen? No. So we have our GFP ranking here. This is a strong base, MEO minus. So it would do an E2 reaction with this if we were to supply that. So just be on the lookout. Like, we're always still in, like, lecture 6 GFP mode for this. So then we do another SN2, and now our CN is going to be on a wedge. Last one here. So overall, we're going from a dash to a wedge. So overall, how many SN2s happen in the whole sequence? One. Now, that has to be in the second step where we have our NaSH doing our attack. That has to be the nucleophile. We're doing SN2. So we need to keep this on a dash. So what should we use? We should tozzle it. Yes. And then it becomes OTS on a dash. So again, overall our strategy is if we want to make an alcohol leave and have the same stereochemistry, we need to do 2 SN2s. If we want to make an alcohol leave and we want to invert the stereochemistry, then we need to have only 1 SN2. Oh my gosh! We've encountered a wild synthesis strategy! So, if we're trying to make alcohols leave, and we see the same stereochemistry as what we want, double inversion, which is like retention. Here we are. Verse, if we want to leave and we want to invert the stereochemistry, just 1 SN2. So, it happens. You know, be careful out there. The grass is tall. Yeah.
So it's just like no stereochemistry change if you're doing 2 SN2s, just like reverse.
Yeah. Like literally, if you invert, it's like turning a light switch on and off.
Is it like a fast reaction? So like, does it like when you have an intermediate, does it still revert? Does it happen
So,
super quickly?
like, I mean, these are just separate reactions, so it's not really about like speed with it right now. But yeah. So now this is a bit of a non sequitur, but can we do another challenge problem just to like knock some things out? So it's not going to be exactly the same thing, but an OH has left, which is why it's in this section. So, what do, where go, how exist?
We got pyridine, so maybe take away a hydrogen first.
Yeah, but before I even start that, before I start doing things, because I didn't always do things, I'm like, where does this fit in to all the reactions that we've been taught? So first of all, I'm clocking, we've done an elimination somehow. I'm clocking a like extended octet phosphorus and then a weird phosphorus boy. Have we seen any of those pieces, any of them elsewhere? We're not even talking about what we're doing yet. Where have we seen things that look like this?
And the SOCl2.
Sulfide and
You get an oxygen from the initial kind of the product.
Okay, I like where you're thinking. Yeah, so like she has gained an oxygen, so that probably came from here. Where did we see a phosphorus with some weird things attached to it? And then Logan made a note of like, oh, and this will spontaneously rearrange and blah, blah, blah. It's going to be like our PBR reaction. Because, again, we're talking about phosphorus chemistry, and we were talking about phosphorus doing these rearrangements. And I think the rearrangement is like something like it'll come like this. And that's, he said, was like a driving force of the reaction. And he was like, we don't care that you know this, but I think being able to clock, okay, phosphorus can do some weird rearrangement things. It's going to be an interesting kind of leaving group for some of our reactions. Do you see how this is going to be kind of similar to this strategy here? Even if we don't know exactly how close it is, that is the thing that we should be connecting to and thinking about. Is there a question? Oh, okay. So, in that reaction, what's the first thing that happened? Well, an OH attacked the phosphorus and kicked off a bromine. So let's try that. The OH attacks the phosphorus, kicks off a chlorine. Okay. Well, then what happened is our second step. Our second step here, the bromine came and did an SN2. But one thing that I see is look at the protonation states here. We have an O minus when we've kicked it off. Whereas if we just kick this off it would be an OH. So why don't we deprotonate it first? So let's bring out our pyridine, deprotonate it. Okay. And now we're pretty close. So we know if we just do an arrow like this, we've kicked off our PO2Cl2, like end product. And we need to create an alkene. So are we doing a substitution or elimination? Elimination. So let's find our alpha, beta positions. So we can deprotonate on either one of these beta carbons. And here we're not going to make you do like a ring, or a chair, I mean, because it's like a 5-membered ring. Like y'all haven't seen that. We're only going to give you cases where on both sides there are going to be accessible hydrogens that could be anti-periplanar. So you don't have to worry about it for a 5-membered ring. For 6-membered rings, you definitely have to worry about it. So I'm just going to have pyridine come and take off the hydrogen on one of these sides. This would fold in and then kick off our PO2Cl2 minus. And that's going to make our two products.
And what type of elimination is this? E2?
E2.
Okay.
Yeah. But again, I think as you'll learn more chemistry, you get into a point where you're like, okay, there are so many things I could do. There are so many errors I could draw. I could deprotonate this. I could do all of this. And the other skill to be working on is clocking, like, what does this look like that I've seen before? How can I base, of all the possibilities that I could do, how can I base my logic based on things I've seen happen as whole reactions? And that is a little bit of a harder skill of, like, a discernment that you're building up. Cool. Yeah, we're going to get through some challenge problems today. Yeah, I forgot about this. Also, I have a sound cue that I made a note last year to add to the soundboard. I have it here, and I have no idea where I meant to use it, so we'll see if it comes up. Yeah, we'll see. So now, we are going to transition. Ethers and epoxides. I'm going to kind of do them together. I'm going to kind of do an abbreviated treatment. I'm not going to talk about everything. I'm going to talk about the most important things. So, one thing that is not real, like nomenclature, chemistry things, but is a tool that I have found very helpful with ethers, is classifying the ether based on the type of carbons on either side of it. So, for this first one, this carbon right here is a primary carbon, and this carbon right here is a secondary carbon. So I personally, Colton Carter, call this a primary plus secondary ether. We'll see why this will be helpful in a bit, but can you take a second and try to classify these other ones? So, tertiary plus secondary, primary plus tertiary, secondary plus secondary. How'd you do? Yay. So, we, with ethers, really only care about making them and breaking them. And it's kind of boring. The go-to strategy that you should think of when you think making ethers is going to be this Williamson ether synthesis. So, in a Williamson ether synthesis, it is the method that can make an any prime plus 1' ether. So if one side of your ether is primary, you can make it with Williamson ether. So which of these would be a good candidate for Williamson ether? Say one more time. 1 and 3. Williamson ether. Williamson ether. So let's talk about why. So the first step is we add NaH, which acts as a base, and that gets us to an alkoxide. And then the second step, we add in a primary alkyl halide. Only really works with primary alkyl halides. Here, it's going to do an SN2 backside attack and kick off a bromine. So this R1, I'm saying this could be any prime. This could be a tertiary, secondary, primary, whatever. And then this R2 is just going to be primary, and that's how we can get either one. So it's made via an SN2 pathway. Now, why does this have to be primary? What if I did this, and now it's a secondary alkyl halide? Then when this goes to react with it, what's it going to do? It's going to do an elimination. Because if we do our GFP ranking, if it's secondary over here, this is going to be fair for SN2. And if we have an alkoxide, we are going to be good for E2. And so E2 would win every time. So the only way that we can guarantee that we're doing the SN2 is by using a primary alkyl halide. Cool. So that's one great way to make ethers, 1' plus any prime. There's also a pretty good method for making a tertiary plus any prime ether. So tertiary plus any prime, we could make 2, and 3 up here using this second method. Okay, what you do here is you add acid and you have alcohols as both your starting materials. The tertiary alcohol, you would protonate it, leaving group would leave, and then you'd have a carbocation. At that point, the R4 can come in and attack, and then you make your ether. So this is an SN1 approach to making ethers. Just like I said earlier, Lecture 7 is all about seeing SN1 and SN2, the remix of like seeing it pop up in other types of reactions. One note, you can also have these molecules be on the same molecule, and that can make a cyclic ether, which you saw a little bit in lecture. But I'm not going to labor on this too much, but just again, we can make it SN2 or SN1. The main strategy that you're going to use in like synthesis is going to be Williamson ether. How to destroy an ether. Again, you can do SN2, SN1. I'll let you read through it more on your own, but the strategy here is we throw it in a vat of acid. And so it's a little bit messy. Generally speaking, ethers are not super reactive. Like, we make things into ethers to make them non-reactive. So we need pretty extreme reaction conditions to break them. But all of that said, when we were talking about making our ethers, we could make a 1' plus any prime, and we could make a tertiary plus any prime. We don't have a really good method to make secondary ethers. And it's because it's going to be fair for both SN2 and SN1. And so, it's hard to make and break secondary ethers. And the piece that explores that and explores some of the ways which we could try and why they fail or why they are hard to do. So now, let's meet epoxides. The epoxides, the most dramatic functional group, if you will. 3-membered cyclic ethers, very strain, much react, explosions, all of the things. You need to know how to make ethers. So you make ethers from halohydrins. Can you say halohydrins? Halohydrins. This is one functional group where it's kind of weird because they're just next door neighbor. So you would think alkyl halide alcohol, but you need to be able to clock halohydrins because they will show up on synthesis. And it's an important thing to clock when 2 functional groups are next door to each other. Whenever you see 2 functional groups or 2 reactive sites next door to each other, think epoxides. Think halohydrins. Also, you can think alkenes, but Lecture 8 is all about alkenes. It's coming. So, with this NaOH base and a halohydrin, you just deprotonate it, make it O-, and then it does an intramolecular attack, kicks off the Br. You'll learn another way to make epoxide in Lecture 8, which is one of my favorite Ochem1 reactions. So, epoxide opening. A couple of things. Broad strokes, when you have an epoxide, you have the option of opening it in base or acid. And depending on where you open it in base or acid, it depends on where the nucleophile adds. So let's talk about acid first. So if we try to open an epoxide in acid, our first step is we protonate the epoxide here, and we have a positive charge. Now, that is going to make the dipole and these bonds even more extreme. And so this oxygen is going to be pulling even more electrons over to it. And we're going to have partial positives on both of these carbons. Now, which partial positive is going to be more stabilized? Is it going to be the tertiary carbon side, or is it going to be the secondary carbon side? Tertiary. So, the side that the nucleophile will go and attack is the tertiary side. And that might seem counterintuitive because you're like, well, the tertiary side's more stabilized, so why would it attack that? And it's because it can already start to be breaking this bond and making a whole carbocation if it's more stabilized. And so it's easier to break that bond is essentially the reason. So our nucleophile is going to come in and attack on this side. And what we see is our nucleophile, if we do like an alcohol and acid, it adds to the more substituted side. And if we use H3O+, an OH adds to the more substituted side for both of these. So these were our nucleophile, whereas our epoxide oxygen is on the less substituted side. So we are attacking. Bloop, bloop. Again, I'm not going to go through the full mechanism here, but I think the big things of acid, nucleophile adds on the more substituted side. And oh my gosh, we made an ether. We discovered another way of making ethers. They just pop up everywhere, don't they? Oh, lecture 8, you might learn a couple more ways of making ethers. I don't know. That'd be silly. That'd be crazy. So, these have more names. So, like, if you have two OHs next door, vicinal diols or glycols. Vicinal, like, vicinity. They're in the same vicinity. They're neighbors, if you will, diols. Again, I think the nomenclature is helpful to be able to clock this as not two alcohols, but as a vicinal diol, which has its own set of reactions, which you'll learn more about next lecture. So now, in base, the main thing that's going to rule which side our nucleophile attacks is just kinetics. And so, in base, the nucleophile is going to attack the less substituted side just because it's faster. Like, there's less steric hindrance, so it's going to attack the less substituted side. So we see if we add an OR minus, like in basic conditions, our OR adds to the less substituted side. And we see that if we add a Grignard, we know Grignards are very basic, they're going to add to the less substituted side. The last note I'll say, and I'm quite actually proud of this diagram. I think it does a good job of like showing all of the epoxide things, and it took forever to make. The other thing I want to say about this is if our epoxide is up on a wedge, then our nucleophile has to attack the antibonding orbital. And so if the bonds are here, the antibonds are going to be down here, below the ring. So both cases, the nucleophile is essentially having to attack from below the plane of the ring. And you're going to have to do some reasoning with that in the problem set on, I think, at least one question that comes to mind. So, yeah.
So it has to attack the antibonding orbitals of the epoxide
Mhm.
oxygen.
That is
Carbon
correct.
bond.
Yeah, to break the bond. Yeah. So now, the practice 3, making ethers and epoxides, I am going to skip. It's just kind of basic practice. I made them myself, so there are extra little practices that you can try doing on your own. But it's just like, how did we make this ether in each of these cases? Or how do we make these alcohols? So practice for your own sometime. But that's all I really wanted to say is the big highlights of ethers and epoxides. Are there kind of any questions on this before we pivot to the last 30 minutes, which is going to be more on the how to study reactions and synthesis? Okay. So we have an issue. And this is the issue that I think actually most people in the class are facing. So in a lot of the student meetings I've had so far, I've just talked through this with the students because I think it is something that will be helpful. You don't have much time and you're getting more and more reactions. And so we need a really time-effective way of internalizing these reactions so they live within you. Because using a study sheet is helpful when you have the study sheet. It is not actually training you to not use the study sheet. So, this I realized last year when I tried to do some branding on this. I realized this is not a universal experience, but did you ever have teachers in the past be like, take your practice exam like you're on a desert island and you have nothing else around you? Have you heard that phrase of like desert island on it? Some yes, some no. So it's not universal. So I think the best way to train you for the real exam, where it's going to be kind of desert islandy, is to do desert island exercise, also called DIES. So, do your daily DIES. Now, what you do, and we are all going to do this together, on a blank page, and actually get a blank page. If you're on a tablet, start a blank page. If you are writing on paper, go to the back cover or something, get a blank page. What I want you to do is for a reaction that you're studying, and we're going to do this, the imine formation reaction, straight up write the starting materials and the arrow for the reaction conditions. Do not draw the product. Do not draw the mechanism. Do not start filling it out on your own before I say begin. So just get to where you have this written out somewhere. So I'm going to talk through what we're doing, and again, we are not writing out the mechanism or the product yet. What we will do is we will start a timer. The timer will be only for 3 minutes and no more. And at the end of the timer, we will go and check our work. In those 3 minutes, what you are going to do is first, try to draw what the product of this reaction is. And second, try to draw the mechanism. I would say do the product first because it's practicing that line reaction skill of just being able to draw the product. And then we're going to do some self-reflection afterwards. So, are we ready? And I'm going to do this as well. I'm going to start a timer. Does everyone have this reaction up? Then I'm going to pivot my screen so you can't see me. I'm going to do it as well. I'm going to see how fast I can do it. So, on our marks, get set, go. One minute left. Three, two, and one. Check your work. Check my work. Grade yourself. Were there any charges that were missed? Were there any kind of curved arrows? Did you get the right product? And the answer to all those questions might have been like, no, I did it perfectly, thank you. But I bet there are some mechanisms where if I said, okay, do nitrile hydrolysis, turn it into a carboxylic acid. I don't know about that. Wow, really going into it. No. Well, yes, but. So, once we do this grading, we've had to kind of sit for 3 minutes, no matter how well we knew this, with like how much we know and don't know. And you can end it earlier if you actually finish it. But like, I actually think that if you don't know what's going on, let those 3 minutes ride out. Just because it makes you sit with the panic that you would have on a test if you were doing that. And that's a really great motivator. Like, it can like destroy you, but it also can be like, like microdosing panic of like, okay, I need to learn this now. When you're reflecting this and when you're stopping, go over and grading it, the only way that this works is if you're really honest with yourself about where things hung up. So even if there was just one step that like just hung for like 15, 20 seconds and you're like, I couldn't figure out what to do for 20 seconds. That's something that the shows like there is a part where you have some doubt or where you're having to reason through instead of knowing it. And so that shows you like, okay, I need to figure out why this step happens. Or like it gives you more information of like, okay, next time I do this, can I get that step a little bit faster? And start off with 3 minutes. I would say get to where you could do most of the reasonable reactions like this level in like under 90 seconds. There are some longer reactions that are going to take closer to 3 minutes, but this is just a really high yield exercise for really doing like active learning of confronting you with what you do and do not know. And I think a lot of students might use something like this as a test, you know, like right before the exam to like test that they know something. No. Use this as a tool to help you learn it. Like it is really, really a time-effective, valuable way. And I've seen students who like have doubled down in this exercise just like soar on exam 2. Because when you know these basics down like the back of your hand, it frees you out to be able to think about synthesis and harder like concepts and how we put reactions together. And if you're still having to think about all the reaction basics of predicting products and mechanisms, it's going to get really hard. It just is when you have 80 reactions. So if you were doing like 30 minutes of these die drills a day, you're going to start cycling through those reactions. And like, yeah, for one reaction, it might take you 3 or 4 to get to where you can do it pretty consistent. But then the next day when you do it, it might only take you 1 or 2, and then eventually you'll get to where you can easily do it in 1. And like, that's the goal. But this is part 1, the basics of the reaction, and you should do this until you feel comfortable to do it within the time constraint. Part 2 of the reaction is we need to connect our basics to how we are going to see it on tests. We need to generalize these basics. So what you do is you repeat the exercise, but do it with molecules that are different. So like here, we did the ones that were given in lecture, so we know what the answer is. Do it with ones that look just slightly different. Change the R groups on the molecules and see if you can still get it. And the curved arrows should be exactly the same as the curved arrows you just did. We just have different chemical groups on our molecule. Now, this seems like it should be basic, but it's actually a skill that needs to be practiced and developed because otherwise it's going to take you a while to see an imine reaction or to see like an imine hydrolysis. And if you feel okay doing all these basic ones, try to do an intramolecular one where both are on the same molecule and it's going to form a ring somehow. Then do the same with the reverse reaction. But you are training yourself to spot this reaction and to apply the basics that you've already learned in a lot of different contexts, which is going to be super valuable for the actual exam. So, why I like this? Active learning. There's a time constraint. You only struggle with it for 3 minutes. You're not agonizing over one reaction for like an hour or something. Flexibility, you can adapt this to your own learning. If you're like, actually, I can like write things pretty quick and I know when I don't know something, so like make it 2 minutes as the exercise. Or if you're like, hey, I have extended time and like it takes me longer to write it out, like do like 4 or 5 minutes. Like you can really adjust it based on your needs. You can also adjust it based on like which reactions you know well and don't know well. So if you're like, okay, it's time for me to start dredging up the lecture 3 reactions because they've gotten a little dusty, then for that you can give yourself more time, but then for these you give yourself less. But I would say never go more than like 5 minutes. And then I just think that they're quite pragmatic. Like, I mean, you can make your copying all the notes, rewatching lectures, you can make flashcards, you can do like reaction summary sheets. Those take so much time. Y'all just don't have it. You just don't have it with the problem sets that we're giving you and with how quickly we move through the lectures. And so I would like high key suggest at least trying it. And maybe trying it this weekend before we meet next week and let me know how it goes. If it doesn't vibe with you, we can think about other strategies to use. But like, I think it's definitely worth trying. So that is my pitch. Does anyone feel like they're going to try it? Oh, we're going to have some, okay, try it out. It might not work, but with the last bit of time. So it is 10 minutes remaining in the actual section time. I did start 10 minutes late. Would you let me go 10 minutes over to get a challenge problem done? If you have to leave, you have to leave. I'm so sorry. Morning section. Yeah, it's on me. It's on me.
I didn't see the annotated ones last week on Canvas.
You mean for section 6?
Yeah.
I haven't uploaded it yet because I just haven't had time. Yeah, but it will be. It will be. Sometime. So, challenge problem 10. Can I get a woof from the audience? Woof. Okay. We put on our best intrepid mindset and we say, what's the first step we do for synthesis? Look at functional groups. Okay. What functional group do I have here? We have an alcohol. What functional group do I have on this molecule? The halohydrin. Halohydrin. Not just an alcohol, not just an alcohol halide, halohydrin. Halohydrin. And so automatically we only know one reaction of halohydrins, so why don't we go ahead and form that into an epoxide. Bloop. And we use NaOH. Okay. Then, what functional groups do I have in the product? So this, what functional group is this? Ether.
An alkene.
And we have an alkene. Now we only know 2 reactions that make alkenes so far. What are they? E1 and E2. Yeah. So we know that this has had to come from a version of it where we have 2 options. Option 1, we have a leaving group on this carbon. Option 2, we have a leaving group on this carbon. And we know that that's going to be E1 or E2. Do you buy that? We've had to do this, like make an alkane via elimination, so we needed to have a leaving group there that we eliminate at some point. Okay. And we don't know which one it is yet, but now we do some brainstorming and mapping, and I feel like I have an anchor point, blah, blah, blah. That's probably going to be the phenyl, isn't it? So in that case, I'm going to make this one up here red star. And then that's going to be this part of the alkene, red star. Okay. Then the other kind of key point that I see is I see 2 methyls. I'm going to make that green star. And that's probably going to be this green star down here. Okay. And then I'm just going to get one more star here. I'm going to call it blue star. And that's where the Br is. That's got to be this carbon. So automatically, when I'm thinking about my goals, one of the biggest goals to bring the molecules together is we need to connect red star to blue star. We need to make a CC bond. And then we're going to make it into like an alkene. But that seems to be our biggest challenge for how to do. Now, let's also do some brainstorming on the alcohol over here. So, the alcohol, what families of reactions could we do with an alcohol? Any reactions? Yeah, we can make them leave. So we could make it into a bromine or a chlorine or an OTS.
NaOET, right? Theoretically, if we want
Sure. I'm just talking about what are functional groups that we can do from the alcohol, because we don't know that leaving group is going to be the right option. So what are other functional like group transformations? What are other reactions that we can do that start with alcohols?
SiO2.
Well, that's already here. We could do some redox. We could take it to an aldehyde or carboxylic acid. We could use what you were saying with base NaH, not NaOH. That's why I got mixed up. So we could turn it into an ether. We could do like acetal. We've even seen alcohols with like ester formation. So we have a lot of things that we can turn alcohols into. And it's not super clear which route to go down. But one thing, when we're thinking about making these carbon-carbon bonds, we need a nucleophile and an electrophile. Now, if we are pretty sure that this is going to form an epoxide, that's the only thing we've seen, right? Is that epoxide a nucleophile or electrophile? Electrophile. So we need to make our red star into a nucleophile. Okay, so ways that we can make specifically the red star carbon into a nucleophile. We're thinking about carbon nucleophiles. Did we see any carbon nucleophiles in like lectures 5 or 6 or 7? I don't think so. Where did we have a carbon nucleophile? Like Grignards. All the way back there. Okay. So we need to think about getting our Grignard involved in this. So also I'm going to do my stars over here, my green and blue.
Did we have to make it into an epoxide? Because we did have a bromine before.
Yeah, but you can't make this into a Grignard because there's an alcohol present. So yeah.
Did you get rid of the alcohol first?
It's going to lead you down a wrong path. Like, if you see a halohydrin, you're going to be making an epoxide at some point, pretty much. Yeah. So, with this, let's see. We need to turn the alcohol into a Grignard. So, let me just go ahead and write what the Grignard we want to be. We want it to be pH MgBr. Well, we could make an MgBr from if we just had a Br, right? Can we turn an alcohol into a bromine? Hey, we learned that, yes. So, let me start listing it out. And when I have official steps, I'm going to kind of do it in black and try to do it out. So, we have our pH, OH. We can use PBr3, make it pH, Br. And then we can use Mg0 and diethyl ether. And then we can do pH, MgBr. Okay, so is our red star a nucleophile? And then our blue star is an electrophile. Now epoxide, if we're in Grignard, is that acid or base? So base epoxides, are we going to attack the less substituted or more substituted side over here? Less. And is that what we want? Yeah, it is. Izzy.
What does that say right above the arrow next to the OH? It's small and underlined.
Arrow next to the OH.
Okay, thank you.
Oh, yeah, sorry. That does look like chicken scratch. Oh, wow. PBr3. Okay, so now let's try combine. Sorry, I realized what the sound cue is for. Wow, sorry, it made me very happy. Combined with ET2O. And then that's step 1. Step 2 is an H plus workup. And so what we get out of it is, I'll go ahead and put it here. So maybe instead of like an arrow there, I'm going to make this like on a long curvy arrow. So we have our 2 carbons, our OH, blum blum, blum blum, pH. We have our red star here. Then we have our blue star here and green star here. Okay. So, do you agree that that is the product that we just did? So now, to make the double bond, we need a leaving group. But now both of these carbons are alkanes. Our route has died. You've been a good one. It doesn't work. We have to regroup. We have to go back to the drawing board. In my notes from last year, I just had add taps to the soundboard. And I had no idea where it was going. I had no idea. And then when it came to me, it made me so happy. So happy. Wow. So, the issue is, we need to have another functional group present at one of these sites in order to get a version where there's a leaving group on one of those carbons for us to do an elimination. So, let's regroup and look more up here. The key thing that I think about when I'm thinking about like multiple functional groups is if we need to have two functional groups next door to each other, I think it's going to have something to do with this epoxide. So let's look back at our epoxide reactions that we've seen. Do you see how so many of these epoxide reactions have two functional groups together? And Grignard's kind of the only one where it doesn't do that. Like Grignard, you just have one functional group and then you've added your carbon thing. So maybe let's look at what else we're missing. The other thing that we're missing here is the ether, which like from this alcohol, we could do the ether, like Williamson ether synthesis. But what if we try to do that ether first? Like, let's just see. Like, again, we're like throwing things at the board. We might have another death. Who knows? So, with this, I'm going to make this also dead. How can we turn this into our epoxide here and then maybe another functional group next door? I said epoxide, I meant ether here and another functional group next door. So we need to make an ether on the more substitute side. So should we do that in acid or base? Acid. And then we need to add whatever our molecule is that forms the ether. So we need to add OET, so HOET. So let's add HOET. And I'm going to start writing this elsewhere. How do I do this in a way that like looks not crazy? I guess I'll just use another color. So if we had HOET and H+, then we have an OET on the more substitute side. We have an OH on the less substitute side. So we effectively accomplish, we have two functional groups that are next door to each other. But the big thing is we still need to connect our red star and our blue star. The red star we've made into a nucleophile, and the blue star is now an alcohol. We already brainstormed our alcohol things. How can we make the alcohol into a functional group that will be an electrophile for a Grignard? What are good Grignard electrophiles? When you first were taught the Grignard reaction, what did it attack? Ketone and aldehyde. Can we make this alcohol and a ketone or aldehyde? Oh my gosh, I think we're onto something. So, if we oxidize it, CrO3 with pyridine, to an aldehyde, then now we can try combining these two in Et2O with an H+ workup. And what we have now is going to be OET, pH, and then we should have an OH formed here at our blue star site. So, do you see how we now have reactivity at these two carbons? So we are going to be kind of in this mode right here. So all we need to do is figure out how to do an elimination that involves an OH. What's your favorite elimination involving an OH? E1 or E2?
Oh, we have our E1 with our, like,
We can conk it. We can conk it. So if we have an alcohol that we're trying to do an elimination with, we can add concentrated H2SO4, and we can get to the product. I'm going to do one alternate way. So if we wanted to, we could also do like SOCl2 pyridine, OET, blah, blah, bum, bum, bum. So it's a Cl now. And then we could do NaOMe, and then do like an E2 version. So this is the E2 route, and this one is the E1 route. Do you see how this game is a lot harder now? We have a lot more things that we can do. And also, if we're having to think about like what are the reagents and how to draw the products, like doing this level of like higher order thinking becomes nearly impossible. So, try out your dyes, see how they go, and remember, sometimes in synthesis, there are going to be fallen soldiers. So, here we are. Thank you for coming to section. Thank you for bearing with me being late. Have a good weekend. I'll stick around for questions. Mm-hmm.